Alrighty folks, we're working here with projectile motion. This video is suitable if you're in a 3C class or a 2D class really. We're looking at this particular application of quadratics. Now, prerequisite skills, if you are working along with us, you need to make sure you're comfortable substituting in values for x. In this case, we might be calling x other letters, but that's okay. Substituting in values and using your bed mass to evaluate. And then you need to make sure you're comfortable with vertex form. That is finding a vertex from the vertex form equation. So, projectile motion. When we're working with projectile motion, typically we have an equation that looks something like this. Now, almost always we'll be working with a negative 5t squared, and that is the coefficient on our t squared. Sometimes you'll see it as x squared, but most of the time we'll use t. The coefficient on this t squared comes from acceleration. Now, everything in projectile motion, that is anything in free fall on this planet, accelerates at the same rate. Now, really, this negative 5, it is certainly an approximation. It'll be the approximation that we work with. This is almost always that we're working with in this class going to be negative 5. All right? Next, what we're seeing here is the initial speed. That is, if we throw something, if we launch something, if something falls, this initial speed is, and typically we're working in kilometers per hour. This is not in kilometers per hour, this is in meters per second, because our height is measured in meters, our time is measured in seconds. This initial speed is the speed that it starts at, which will change as the model goes along, but this is the starting speed that we're working with. And really, this is the starting up-down speed, but no, we're not going to worry too much about that. And then we have our initial height. All right, so everything that's tossed is going to be tossed from a certain height. Sometimes that height could even be 0, but in this case, the height would be 5. In this case, the initial speed would be 20, and as always, our acceleration is going to be negative 5 right here. Now, we expect, if we're throwing something, or if something is launched, we expect its pathway through the air to look something like this. Now, you'll notice, you might be used to seeing a pathway like this if you're watching a throw from a profile viewpoint, but really, this is time. So what this story is really telling is, okay, where time equals 0 right here, we're throwing something from a certain height, and then it's going to go up, and then it's going to hit its maximum height, and then it's going to go down. And that's the story over time that this sketch on a Cartesian plane is really showing. And we can expect that every single time something is thrown, all right? So we have here a ball is thrown into the air. The height of the ball in meters is represented by this equation. And we notice this equation looks very, very similar, where it has this negative 5t squared at the start, and then it has a 25t, which we know how to interpret, and it has a plus 6, all right? So the initial speed of the ball. Well, hang on. We actually don't need to do any work in order to find that. We just talked about how the initial speed is right here. It's the coefficient. It's the number that's in front of our t value, not the t squared value, the t value. My apologies. Now, if we're working down here, we can see, hang on, this speed is just shown right away in our equation. Our speed that we're working with is simply 25 meters per second. That is, it's the coefficient, the number, that's right in front of our t term, or that is a part of our t term, or that's a part that does not have t squared, but it does have a t in it, all right? So, from what height was the ball initially released? Well, hang on, we also know how to do that, because we already talked about initial height. That's going to be the number that's added to the end, or rather, that's going to be the number that has no variable on it. So in this case, our initial height is 6 meters. Now, how high was the ball after 3 seconds? We're going to need to do a little bit of work in order to accomplish this, right? So we have this equation, and this equation tells us the certain heights at different times. Well, we can just substitute in our value after 3 seconds. That means t equals 3. So we're working with the height is equal to negative 5 times 3 squared plus 25t plus not t3 plus 6. And then we're just evaluating this using our bed mass. So we need to work with our exponents first. This is negative 5 times 9. Plus 25 times 3 plus 6. Good job, us. Then we're handling our multiplication. That's negative 45 plus 75 plus 6. We're running out of space. We'll keep working over here. That's negative 45 plus 75. Now we're doing our addition and subtraction, and we're working with 36. All right, so our height is 36. 36 what? Oh, 36 meters, okay? Now, I'm actually going to go ahead and just put that right into my table of values right there. And I can put this down maybe in a little bit of a circle here to emphasize, is my final answer. How high was the ball after 3 seconds? It was 36 meters high. And then we can graph the height of the ball on the axis. In order to do that, we'll need to fill in our entire table of values. I want you to pause the video, substitute in these different t values, unpause, see how you did. Good, okay, so we have all of our points here. Now just be wary of this final one, this final height. We'll see what happens. I want you to, now that you've checked your t and h values, I want you to, again, pause the video, start plotting these on your Cartesian plane, see what happens. Good, okay, and we notice this final point, it would not fit. It would be way down here somewhere. That's okay, we're not interested in that. As soon as these h values become negative, they're no longer meaningful, right? Because if we're throwing something, in this case we're throwing a ball, a negative height doesn't really make much sense unless we have a whole bunch of other context around it. So we can assume that at some point in between 5 and 6 seconds, our ball hits the ground, which makes sense if I follow through with our parabola here. Okay, it hits the ground, and as soon as it hits the ground, then its job is done. Let's clean that up a little bit. Now something else to notice, because these two heights are exactly the same right here, does that mean that the ball is just staying still in between 2 and 3 seconds? Well, hang on, I've never seen a ball do that when I throw it in my life. What's actually happening is the maximum that the ball is reaching is directly in between those. It will be above 36 meters, we know that, but we don't know exactly how high it is based off of all the work we've done so far. So we have ourselves with this shape that shows us this is a parabola, it is facing down, that's what we expected. Nice work, folks. Next question. We notice, okay, so the height of a flying shoe is modeled by this equation. H equals -5 times t minus 3 squared plus 55, where h is the shoe's height above the ground in meters and t is the time in seconds. Do we know why the shoe is flying? No, we don't. That's okay. We will notice, though, this form's a little bit different. This form does not look like what we were working before. Let's try and show them both on my screen. I apologize. There we are. This form is not looking like what we were working on in our previous question. Way up here, this form is in standard form that we've seen. Down here, this is in vertex form that we have worked with previously. Remember, that was one of the prerequisite skills here. Does this form tell us the acceleration? Does it tell us our initial height? Does it tell us our initial speed? Maybe not. Maybe not all of those. But that being said, it can tell us some information really quickly. Remember, it's vertex form. It tells us the vertex. What's a vertex? Oh, it's a maximum. So in question A, if they're asking us how many seconds will it take for the shoe to reach its maximum height, remember, this general shape we're working with, the vertex, would be at +3 seconds and a height of 55 meters. Okay, so that's way up here. There's our vertex. We're expecting a quadratic that opens down something like this. This is super rough. That's fine. If they're asking us, how many seconds will it take to reach its maximum height? Oh, that's easy. That's just the horizontal coordinate. That's just our 3 right down here. So we know it will take 3 seconds. What's the maximum height of the shoe? Oh, the maximum height, we've already found that. That's from the vertex because this is in vertex form. The maximum height is 55 meters. Why this shoe is flying, I'm not sure, but whoever tossed it has one heck of an arm. What is the height of the shoe 5 seconds after it was thrown? In order to calculate this, we know if it's 5 seconds after, then our t equals 5. And we have our equation that we can work with here. Again, we'll follow our bed mass. Our bed mass will look a little bit, following our bed mass will look a little bit different right here. Whoops, instead of t, we're going to be working with 5, right, minus 3, because our t equals 5 right here, squared plus 55. It'll look a little bit different because this is in another form. There's some other steps to follow. This time we have some steps within our brackets we will need to respect. We're working through. Nothing in particular is challenging in a new way right here. We're just following our steps as we have learned. So -5 minus 4 plus 55. We're performing our multiplication. That's -20 plus 55. Okay, so we know that our height is 35 meters. Now, I'm hoping at this point you feel a little bit more comfortable working with some application questions in projectile motion. We're working with our quadratics here. Nice work, folks.